Alright, AP Calc, welcome back. Today we're going to go over differentiability. Differentiability is the ability to take the derivative, and we're going to go through our classwork here. So first off, differentiable. A function is differentiable if it is continuous and smooth. A function is smooth if it looks like what you would expect. You can maybe run your hand along it and there's no points, no jagged edges. It is smooth, as opposed to something like this, which is jagged, which is pointed. That is not differentiable at those points. Corners, cusp, vertical tangents, and discontinuities are places where the derivative does not exist. And we're going to go through each of those. So a corner is exactly what you expect, like the corner of a wall. And the corner is defined as a place where the tangent, the slope of the tangent as we come from the left side is different than the slope as we come from the right side. You can see we would have two different values. A corner does not need to be made up of straight lines. It could be made up of a curve, such as this, and then maybe a straight line. And if the slope is different when we get to that peak, then as on both sides, then it's not differentiable. A cusp, picture of a cusp looks something like this, and the difference is that for a cusp, the derivative coming from one side would be different than would be negative infinity going from one side and positive infinity as you come from the other side. So if it's going like this and steeper, and then on the other side it's positive, so one side is negative, one side is positive, then it is a cusp. So it could be like that, or it could be something like that. That would also be a cusp. A vertical tangent is a tangent line to a curve where it's going to become vertical, and the slope is going to approach either positive or negative infinity. So here the slope is approaching negative infinity. It doesn't matter if you come from the left side or you come from the right side. There is the tangent line. We have four different types of discontinuities. The first one is a jump, which we know what that looks like. There's a point and we're making a jump. The second one is a removable, which means a point is taken out. And then we have the infinite, which means we have a vertical asymptote, something maybe like this. And then we have the oscillating, which sine of 1 over x is an example. So it kind of waves back and forth, and then it gets really crazy. And so this place where it gets crazy is the oscillating discontinuity. So the first thing we want to do is to be able to identify each of these types. For each graph, determine if the function is differentiable, if it's smooth. If not, classify why the derivative does not exist. So if you're looking at the first one, does that look smooth? No, it's not. So we're going to say no, this is not differentiable. We could also say non-differentiable, although that's pretty long to say here. So you could just say no. If not, what do we have here? We have a corner, and the corner is when x is equal to -1. The second one here looks pretty smooth, so that is differentiable. And there's no corners to it. There's no corners. There's no cusp. Number 3, is that smooth? Well, it's just a line, so that is differentiable as well. I'm going to abbreviate it, diffy. What about number 4? That looks similar to number 3, except what's the difference here? Oh, there's a point that's removed. So this one is not, because we have a removable discontinuity. And that removable discontinuity is at x equals 1. Continuing, for number 5, is that going to be differentiable? Well, there's a problem. Does everyone see where the problem is? The problem is right here. There is a vertical tangent. So this one is not differentiable. because we have a vertical tangent. What about for number 6? Do you think that's differentiable? Is it continuous and smooth? It's not even continuous, so this one's not differentiable either. We have a jump discontinuity. And that jump discontinuity is when x is equal to 2. What about number 7? Is that differentiable? Does it look smooth? No, it's not differentiable. And which one do we have here? This is going to be the cusp. This is a cusp because as we come from this angle, from this side, the slope would be negative infinity, but when we come from this side, the slope would be positive infinity. So this would be a cusp. What about number 8? Any problems with number 8? Is it smooth? Is it continuous? Yes, this is differentiable. So this is differentiable. And we have horizontal tangent, but horizontal tangents are okay. The slope is defined here. Whereas for 5 and 6, infinite slope or negative infinite slope is not defined. So those are why it's not differentiable. And 2 more. Number 9, we have, is it continuous? It's not even continuous. So this one is not continuous. This has an infinite discontinuity at x equals 2. And what about for number 10? Is that differentiable? Again, it looks like it comes to a peak. Here, it's not quite smooth. Here we have a corner. So this one is no. Just write no here. And we have a corner at x equals negative 2. A function is differentiable if we can take the derivative from the left side, and we can take it from the right side, and we get the same answer. A continuous, smooth function is differentiable. So differentiability implies continuity. Going a little bit further, differentiability implies that it's locally linear, which implies that it's continuous, which implies that the limit exists. This only goes one direction because we can have something where the limit doesn't exist. That's not continuous. We can have something that's continuous, which is not differentiable. Let me explain what this locally linear part means. You pull up your calculator and you type in y equals x squared, and you look at the graph. The graph looks pretty much like a curve, like a parabola, a quadratic. But if you zoom in to one particular spot, or any spot on the curve, if you zoom in, what happens? It looks a little less curvy, doesn't it? And if you keep zooming in on one spot, it's even less curvier. And I can continue zooming in indefinitely, more and more. And eventually, it looks almost like a line. So that's what we mean by locally linear. If you would zoom in more and more, then it looks like a line, which is what we have going on here. All right, on this page, we are going to look at each of these functions. We're going to graph them, and we are going to determine if they're differentiable at x equals 0 by using the calculator. And just by examining, determine if we have a corner, a cusp, a vertical tangent, or some kind of discontinuity there. So our first one is cotangent of x. So let's bring up our calculator. So here's our calculator, and we're going to type in cotangent. Well, there's no function for cotangent, but we should know that cotangent is 1 over tangent of x. Look at the graph, and this is what we have. The graph of cotangent, and look at x equals 0. And what's going on here? We have a vertical asymptote. Asymptote, you would say no, this is not differentiable. We have a vertical asymptote. Or, of course, we can also call it an infinite discontinuity. at x equals 0. All of these are going to be at 0, so we don't really need that part. So we have an infinite discontinuity at x equals 0. Let's go to our next one, x to the 2/3. Okay, here we typed in x to 2/3 and graph it. And what do we notice about this graph? What's happening here at 0? Does it look like it's smooth? Here we have a cusp. So again, here's our sketch. And this one is an example of a cusp at 0. So no, this is not differentiable either. Graph, is this differentiable at 0? So if we look, does it look like it has a slope, a well-defined slope at 0? This one has a vertical asymptote. This one has a vertical tangent. So this has a vertical tangent at x equals 0. So no, this one has a vertical tangent. Graph, type it in, graph it. Here we have a quartic. Is this one differentiable at x equals 0? Should be able to see that this one kind of looks like a W. This one is differentiable. So you can put yes there, put differentiable. Number 15, we're going to graph y equals absolute value. Absolute value, go over to num, right there at the top. Absolute value of x, subtract 4x on the outside. Graph. If you look closely, it might look at first like it's a straight line, but do these slopes exactly match up? I don't think they do. I think they bend a little bit. So for this one we have a line, we have another line. This one's giving us a corner. The slopes are not exactly the same. The last one here, this is called our step function, also called a floor function, also called the greatest integer function. Gives us the greatest integer less than or equal to whatever the input is. And when we go to the calculator, it's going to look like int. So let's go ahead and type it in. When we go to math, go to num, and it's down at number 5, int of x, graph, and you can see it looks like stair steps. So this one looks like stair steps. So this one is not differentiable because we have a jump discontinuity at x equals 0. Okay, on this next page, I'm going to show you how you can take the derivative with the calculator at a point. I'm going to work through the odds here so that it gives you a chance to do the evens. And I'll show you how to use the calculator to get the derivative at a specific point. So let's pull up our calculator. Calculator open, and we are going to go to the math menu. And we're going to go down to number 8, where it says in derive, or in derive. And this is what it looks like when you open it up. If you have a newer calculator, you should have this little template, which makes it very easy. The first thing we're going to do is put an x in the bottom there. So we're taking d dx, that's the derivative. Inside the parentheses, we need to take the function that we're taking the derivative of. In this case, our first one is negative x squared plus 8x minus 13. And we want to take that derivative when x is equal to 3. Then you simply press enter, and we have the derivative when x is equal to 3. The derivative is 2. Okay, so here it is for 19 as well. Again, we go to math. We're going to go down to number 8, take the derivative, type in our variable, type in our function in the parentheses. You have to make sure it's in there. Do not type outside of those parentheses. So here we want x cubed, and then plus 9x squared, plus 24x, plus 17, And we want the derivative at x equals -3. And here we get negative 2.9999 repeating. So what does that mean? Well, sometimes when doing this operation, the calculator makes a slight error. So if you get a number that appears like this, you might have to round it. So this is pretty close to -3, and that's what the actual answer is -3. So keep that in mind when you're using this, that the calculator is performing some algorithm in the background. It might have a little rounding error, so you have to make your best guess as to what the actual derivative is. Again, math, number 8, d dx, and this time we have a fraction, so negative alpha y equals to bring up our fraction bar. On top we have 3, on the bottom we have x minus 1, and here we want the derivative when x is equal to 3. Oops. Out here. And that gives us 0.7500001875. So again, what is this relatively close to? I mean, you can tell here at the end it's got a little bit of error going on. It looks like that's pretty close to 0.75, and we're going to round it to that. The derivative here is 3/4. Usually we'll want to give our answers as fractions. In AP Calc, if you do give answers as decimals, you should be going to 4 decimal places if needed. For the last page is just true and false using the definitions that we talked about and the theorem. We'll go through a few of these so you get the idea. 23 says if f is differentiable at x equals a, then f is continuous at x equals a. So sometimes, I like to think of an example. If I have a differentiable function, I know it's going to be continuous and smooth. So does that mean it's continuous? Yes, it does. 25 says if the limit as we get closer to a exists, then f is differentiable. So is that always true? If it's always true, you circle true. If it can be false, though, then we circle false. Can we have the limit exist but it not be differentiable? I think we can, right? So there the limit would exist, and it's not even continuous. It's not differentiable. So this one would be false. And that also goes with 27. If the limit exists, does that show that the function is continuous? Well, using our previous example, we can have the limit exist without it being continuous. So that one would also be false. All right, I'd like you to do the rest of them, and if you have any questions, let me know. Bye!